So, conservation equations and analysis of finite control volume. So, in this chapter we are going to discuss now equations which will help us in dealing the issues by considering control volume approach, because these problems can be solved with the help of differential equation or with the help of control volume approach. So, many times we use control volume approach. So, we will try to write equation in the form of by using concept of control volume. We will try to understand some differential equation also in this chapter which deals with the dynamic issues. So, for that we will first study the systems and control volume, which we have already studied in detail in thermodynamics. In thermodynamics we have studied that what is the meaning of system. This system is known as a identified area in which we want to focus our study. So, this system is divided with the help of some boundary to the surroundings. So, after the boundary we have a surroundings, and inside the boundary we have a systems. We may have generally these three type of system. One is called closed system, another one is called open system, and third one is called isolated systems. So, we will try to understand what is the difference between these three. This is a closed system in which the energy can interact through these boundaries. So, energy can go inside the control mass, energy can go outside the control mass, but mass cannot come in and mass cannot go out. This mass of system remain fixed and their identity also remain fixed. This is the meaning of closed system. Then we have a control volume system. Control volume system, their boundary is defined and mass can enter into the control volume, mass can go out the control volume, energy can go inside the control volume. Similarly, energy can go out the control volume. So, energy as well as mass both can interact through control volume. In isolated system where there is no interaction between the system and surroundings, means no mass and no energy can interact with the surroundings. So, first we are going to discuss conservation of mass, or which is in terms of the fluid mechanics we call it continuity equation. The conservation of mass, we know that mass cannot be created, cannot be destroyed. So, for a control volume it may be written in this sense that rate at which mass enters the region for a given control volume is equal to rate at which mass leaves the region plus rate of accumulation of mass in the region, right. So, this can be written on the basis of conservation of mass. So, suppose this is a region control volume, their mass is entering into this region and this mass is leaving the region. Now, we can write continuity equation in differential form. Differential form means we will write the equation in the terms of the velocity gradient and the pressure and density, right. So, if we have a compressible fluid or incompressible fluid, then pressure and densities are dependent to each other, but here we will not bring term pressure, we will use the term densities. So, we have a Cartesian coordinate framework where we have a x direction, this is our y direction and this is our z direction. In the fluid region we have a parallelepiped written as A, B, E, F and C, D, H, G. So, this is a chosen control volume in a fluid region. Now, in this control volume we have a fluid flow happening in x direction, y direction and z direction. So, if we assume that fluid is entering through phase A, B, C, D in x direction and fluid is entering in x direction with velocity u. So, what is the mass flow rate going in the control volume through phase A, B, C, D will be equal to rho, rho is the mass density, mass per unit volume into u multiplied by area of this phase A, B, C, D. Now, area of this phase we have the dimension of this parallelepiped in x, y, z direction as dx dy dz, where dx dy dz are the dimension of infinity small size. Now, this mass which is entering in x direction with velocity u is going out through face E, F, G, H in x direction. So, with the help of Taylor's expansion series, by neglecting the higher order term, we can write what is the mass flow out through face E, F, G, H will be equal to rho plus del rho over dx into dx. So, what is del rho over del x? It is a gradient in x direction, density gradient in x direction. So, it means we are assuming that density is varying in x direction. So, rho plus del rho over del x into dx, because dx is the distance in x direction, multiplied by velocity. Velocity is also variable, u plus del u over del x into dx multiplied by area. Area is equal to dy dz. So, mass entering in x direction is equal to rho u dy dz, mass going outside in x direction through face E, F, G, H is equal to this quantity rho plus del rho over del x into dx multiplied by u plus del u over del x into dx multiplied by area of this face. Area of the face is equal to dy into dz. On the similar principle, we can write that what is the mass going in the control volume in y direction, what is the mass going outside the control volume in y direction, what is the mass going inside the control volume in z direction through this face, bottom face C, D, H, G, what is the mass going outside the control volume through face A, B, F, E, right. On same principle we can write.